Okay, hello and welcome to this chapter 7 video for S2, hypothesis testing, where we test hypotheses, see if they're correct or not. Let's do this by looking at a few examples. The more examples you look at, then the clearer and the more sense this topic makes. So bear with me for the first few until you start seeing the patterns. The first example I'm going to do about flipping a coin. Let's have X be the number of heads this coin gets. We're going to flip this coin 10 times, so we assume that X is going to be binary distributed with 10 here. Now the test here is what the probability of getting a head is. Now if this coin's fair, we might assume that the probability is going to be 0.5. So this might be our initial hypothesis, our null hypothesis, H0, the null hypothesis is the probability of this coin getting a head is 0.5. But maybe someone's seen me flip this coin a few times and actually they think it's a biased coin, maybe it's an unfair coin. So the alternative hypothesis is something else you believe may be true. So this person perhaps thinks that the coin is biased towards getting ahead, therefore probability is more likely to be bigger than 0.5. This is called the alternative hypothesis. Essentially what we're doing is we're pitting the null hypothesis up against the alternative hypothesis and saying which one's more likely to be true. So this is the one we believe is most likely to be true at the minute, and then we're testing go, actually, do you think it's more likely that it should be picking a bigger number? Now the alternative hypothesis is always more vague. It's just bigger than or smaller than. The null hypothesis is always equal to. This could also be not equal to. We'll do those 3 different types, bigger than, smaller than, not equal to in turn. So we'll do a bigger one to begin with. So now we actually need to get some observations, because it's really hard to tell whether this is this one or this one without any data. So let's imagine I've now flipped this coin 10 times. In fact, I did this earlier just to keep the time of this video down short, so I didn't do it on video. So I got a head, then a tail, then 2 more heads, then a tail, then another head, then a tail, and then 3 more heads. And if I can count correctly, yeah, that's 10. And if you count the heads, there's 7 there. This 7 here, otherwise known as a little x, is our observed value. So that's what you actually happened in the one time you did it. Now, hopefully you realise that it's possible to get anywhere between 0 and 10 heads. If being that either of these two situations is true, even if it was 0.5, you could get lucky and get 10 in a row. There's that Darren Brown video where he flips coins for hours and gets 10 in a row. It is possible, but obviously it's unlikely. And the test really is saying, is it likely or not to get this many heads? If it's really likely to get this many heads with the probability of 0.5, then we're probably just a bit of a fluke chance of getting that many heads. But maybe this is a really large number of heads, and maybe it's more likely that it's got a probability bigger than 0.5. And the test is, well, which of these two things do we believe most? So you have to choose a level of significance. So all the tests in S2, and pretty much all the tests you'll see with hypothesis testing, are a 5% level of significance. That's what we're testing against. We'll come back to that in a second, but we'll see that 5% figure coming up soon. So what we're looking at now is what's the probability that my number of heads happen to be 7 or more, because 7 is quite a lot of heads. I mean, you flip a coin 10 times, you're splitting 5. 7 is quite a lot. What's the probability that I would get 7 or even more than that? Let's work that out. So it would be, what, 1 minus probability of getting x less than 6 is just like a normal binomial question now. 1 minus, we've got to look at what's the probability of getting 6. Let's have a look here. So we've got n is 10, x is 6, go along to the last column. The last column is probability of 0.5. That is 0.8281. 0.8281. Yeah, that's all good. 1 minus that is what, 0.1719 if I'm not mistaken. So that is what, 17.19%. Now what we do is we compare this number, this 5% number here, and whether that number is bigger or smaller than that one depends on whether we keep the null hypothesis as being most likely, or we think actually that's very unlikely and change to the alternative hypothesis. So let's just look. If x is equal to x, so this little x is our observation, so in this case it's 7. If the probability of x being bigger than x is really small, that would mean it's highly unlikely that this hypothesis is true, because the chance of it being true is less than 5%. And so therefore we would reject our null hypothesis and in favour take the alternative one as being true. So we would choose H1 instead, and probably is more than 0.5. The alternative then is that the probability of X being bigger than our observation is greater than 5%. So here's choices. Either it's less than 5% or it's bigger than 5%. If that number is bigger or smaller, depends what we do. If it's bigger than 5%, that would mean the chances of X being bigger than our observation 7 is actually really likely, and therefore it's more likely just to be a sort of a situation where we just happen to have got a few more heads than is the norm. So therefore we would keep our original null hypothesis H0. So let's have a look. Here we've got 17%. So the chance of getting 7 heads is quite likely, and therefore it's more likely that the original 0.5 is correct, and we keep our H0. All we're doing is comparing that 17 to the 5% and going, what's bigger than 5%, therefore we're keeping H0. Okay, that wasn't too bad. Let's have a look at something else. Let's say that Y is the number of games of pool I've won when I'm playing against my brother. Let's say that each game is independent of the last, and that means that it's binomially distributed. Let's say I'm going to play my brother 20 times over the next few weeks at pool, and the probability of me winning, well, he's actually better than me. So at the minute we think it's 0.4. He beats me slightly more times than I beat him. And let's see if that's correct or not. So the null hypothesis is that probability hasn't changed, but actually we played several games of this pool. We played 20, and I only won 3 of them. So it's quite likely that maybe probability is less than that. So our alternative hypothesis is the probability is less than 0.4. So different to over here where it was more. So this time we play pool, and it turns out that after these 20 games, I won 3 times. So he won 17. So maybe 0.4 is a bit much. Maybe H1 is correct here. Let's have a look. So let's again do a 5% level of significance. So let's work out the probability. Now, here we did more than 7 because we were looking at the probability being bigger than 0.5. So obviously we're aiming in that direction. Here, because the probability is less than 0.4, that's our alternative hypothesis. We're interested here in how many times I get less than what we're expecting. So on the other side. Y being less than 3 is an easy one to do. We just find the table. There it is. And then we look up when n is 20 and x is 3, probability of 0.4, which is that column just there. Oh, we see that 3 is what? 0.0160. 0.0160. Oh, there we go. Things are falling over. So that's what, 1.6%? So this time we're looking at not bigger than, but probability of y being less than y both times. And then asking whether that is a small chance or a big chance. So here, 1.6%. So if this was really the probability, the chance of this happening is only 1.6%. So it seems unlikely to happen just by chance, right? It's less than 5%. So here we should reject H0. Here we should keep H0. So I think here we try to reject H0. It's probably more likely that the chance of me beating my brother is less than 0.4. I'm being too good to myself here. So we've now take H1 as being our new hypothesis, and we try maybe to choose another value, P being from 0.3, and then seeing if the next 20 games it was statistically significant. That's the first 2 types. These are called one-tail tests because we have one side or the other side. We're looking at one side or the other side. In the next video, we'll look at 2-tailed tests where the probability here is not equal to, and see how we deal with those. But until then, have fun.